This part of the course will be about modeling dynamic systems. Mathematical models are indispensable in analyzing systems and in many stages of engineering design process. To start with, note that a basic trade-off in modeling is simplicity versus accuracy. In other words, to have more accurate models, you have to increase its complexity. Linear models offer a fair trade-off in this sense. By changing the number of parameters in your model, you can have simpler or more accurate ones. Let us recall the definition of a linear system. Assume that y1 is the output of the system corresponding to the input u1, and y2 is the output corresponding to u2. For the system to be linear, you need two conditions to hold. Firstly, the output corresponding to the sum of u1 and u2 should be the sum of the corresponding outputs, that is, y1 plus y2. This property of linear systems is known as the superposition property. Secondly, if you multiply the input to a linear system by a scalar, the output is also multiplied by the same scalar. That is, a times u1 will yield a times y1 as the output. This property is known as the homogeneity. We are going to use linear differential equations as mathematical models of dynamic systems. In many cases, our differential equations will have constant coefficients. Occasionally, the coefficients may also be functions of time. The former case will correspond to linear time invariant, in short LTI systems, whereas in the latter case, we'll have linear time varying, that is LTV systems. Before considering linear models, let us discuss briefly the nonlinear ones. A model, or rather a differential equation, will be nonlinear if you have nonlinear terms in it. For example, terms such as the square of derivatives or products of different derivatives, or nonlinear functions like cosine, sine, logarithms, etc. In some cases, you can have nonlinearities which cannot be expressed in a closed form. The saturation type of nonlinearity is, for example, one of them, where the output depends linearly on the input for smaller values of it, but becomes saturated for higher values of the input. The dead zone nonlinearity is another example, which is quite common in flow systems, especially in valves. Finally, here is a graphical representation of square law nonlinearity, where the output is proportional to the square of the input. Coming back to linear models, the most commonly used linear frequency domain model for dynamic systems is the transfer function. It is defined as the ratio of the Laplace transform of the output to the Laplace transform of the corresponding input under zero initial conditions. Naturally, since the transfer function is a ratio of two Laplace transforms, it is denoted as a function of S. Consider a linear time-invariant single input, single output system represented by such a differential equation. Here x is the input signal and y is the output, and the coefficients a's and b's are constants. We assume that the order of the highest derivative in y is larger than the order of the highest derivative in x. That is, n is larger than m. Now, take the Laplace transform of both sides of this equation. Remember, we assume that all initial conditions are zero. So, effectively, derivatives will be replaced with multiplications of the Laplace transforms of y and x by s. Taking terms in the left-hand and right-hand side of the equation into parentheses of y of s and x of s, we can obtain the ratio of y of s to x of s. In other words, the transfer function of the system represented by this differential equation. At this point, we can note several properties of transfer functions. First of all, It is clear from the derivation that the transfer function is a representation for linear, time-invariant, single input, single output systems. Also, it is a mathematical model relating the input directly to the output. Note that the transfer function we have denoted as g of s is independent of the input. It does not provide any information on the physical structure of the system. That is, we do not know whether the transfer function above is referring to a mechanical system or electrical system or a thermal system, for example. Nevertheless, if the input is given, you can obtain the Laplace transform of the output by multiplying the transfer function with the Laplace transform of the input. On the other hand, you can obtain the transfer function of a system by studying the inputs and the corresponding outputs. That is, you can apply an input and measure the output, and then you can obtain the transfer function by building the ratio of their Laplace transforms. Transfer functions can also be obtained by exploiting the physical relationships between the input and the output of the system. Here is a simplified example. Let us consider a satellite orbiting the Earth, which we are going to represent by this diagram. The attitude of the satellite is defined as the angle of its axis with respect to some fixed reference and is denoted by theta. To rotate the satellite around its center of mass, one would use the thrusters located at A and B. They are of distance of L from the center of mass. Each thruster is assumed to provide a force of capital F over 2. So the torque applied to the center of mass by the thrusters is F times L. Now we would like to find the transfer function from the torque, that is the input of the system, to the angular position theta, which is the output of our system. The transfer function can be obtained as the ratio of capital theta of s to capital T of s, where capital T of s is the Laplace transform of the torque function and capital theta of s is the Laplace transform of the angular position theta. In this simplified example, this ratio can be obtained using Newton's second law, namely the moment of inertia of the satellite multiplied by the angular acceleration is equal to the torque applied. If we take the Laplace transform of both sides, under zero initial conditions, of course, we can write the transfer function theta of s to T of s as equal to 1 over Js square. Here, the fact that the transfer function has two s factors in the denominator means that the angular position is to be obtained from the torque input by double integration. Here is another example, a parallel RLC circuit. Let us now obtain the transfer function from the input current to the output voltage. In doing this, we are going to denote the Laplace transforms of the output voltage V, the input current I, and the current in the resistor R, namely I sub R, with their corresponding capital letters. In fact, the transfer function of this circuit can be obtained directly if we consider the impedance expressions of the elements. We know that V is equal to R times I sub R by Ohm's law. So what we need to do is to write the resistance current in terms of the input current using the current division principle. And then the ratio of V of s to I of s can be obtained as RLS divided by RLC s square plus LS plus R. Note that this is a strictly proper transfer function and the denominator degree is 2 since we have two dynamic elements in the circuit. Now let us consider the transfer function g of s of a system with output y and input x. It follows that the Laplace transform of the output of the system can be obtained as g of s times x of s. and by the convolution property of the Laplace transform, that would correspond to x of t convolved with g of t, or g of t convolved with x of t. Of course, here small case g refers to the inverse Laplace transform of the transfer function g of s. Now, if the input is the unit impulse function, that would mean that x of s is equal to 1. Hence, the response of the system in this case would be simply g of s. In time domain, that would mean the output is equal to the inverse Laplace transform of the transfer function, which we had denoted as small case g of t. That's why the inverse Laplace transform of the transfer function is also referred to as the impulse response function. Taking now the idea of using transfer functions as mathematical models of dynamic systems one step further, we will consider the block diagrams. A block diagram is a pictorial representation of transfer functions belonging to each component in the system and of the flow of signals. In drawing block diagrams, we will need three sorts of symbols, namely blocks, summing points, and branch points. Blocks represent the input-output relationship of the components with their transfer functions. The input signal is shown by an incoming arrow, and the output signal is shown by an outgoing arrow. In a summing point, whether the signals are going to be added or subtracted is shown by plus and minus signs on the incoming arrows. In some cases, there may be more than two input signals on a summing point. On the other hand, branch points are for copying signals so that they can be inputted to more than one component. The first block diagram we are going to consider shows a basic feedback configuration. In such a feedback connection, the feedback path can be a unity feedback, or it can contain a transfer function which we will denote as h of s. On this system, we can define three different transfer functions. The first one is the open loop transfer function, which is the product of all blocks in the loop. In this case, g of s and h of s. In other words, it is the transfer function from the signal E to the signal B. The second one is the feed-forward transfer function, which is in general the product of all blocks from the input R of s to the output C of s. In this case, we have only G of s on the path from R to C. The last one, maybe the most important one, is the closed-loop transfer function. That is the transfer function from the input R to the output C. To derive the closed-loop transfer function, first note C of s is equal to G of s times E of s, and the signal E is the difference between R and B. Here you can replace B with H times C. We can substitute this expression for E in the equation on the left-hand side to obtain C of s is equal to G multiplied by R minus H times C. And now, rearranging this equation, the ratio of C of s to R of s can be obtained as G over 1 plus G times H. Note that the closed-loop transfer function is obtained as the feed-forward transfer function divided by 1 plus the open-loop transfer function. Another important point we have to emphasize here is that we are considering a negative feedback configuration. If the feedback were positive, then the denominator of the closed-loop transfer function would be 1 minus the open-loop transfer function. Next, we will analyze a block diagram where we have two inputs, namely the reference input R and the disturbance D. Since this is a linear system, we can obtain the output C of s using the superposition principle. So the output will have two components, C sub D and C sub R. C sub r is the component that is caused by r of s only. In other words, whenever the disturbance d is equal to 0. And C sub d is the component that is caused by the disturbance only. This corresponds to the case where the reference input r is equal to 0. First, consider the case where d of s is equal to 0 and redraw the block diagram. Remembering that the closed-loop transfer function can be obtained as the feed-forward transfer function divided by 1 plus the open-loop transfer function, we can write the ratio C sub r to r as g1 times g2 divided by 1 plus g1 g2 h. Now consider the case where r of s is equal to 0. In this case, the feed-forward transfer function is only g2 of s, and the loop transfer function is g2 times g1 times h. So the closed-loop transfer function C sub d by d will be g2 divided by 1 plus g1 g2 h. It is interesting to note that both closed-loop transfer functions share the same common denominator, namely 1 plus the open-loop transfer function. In fact, this is called the characteristic function of the system, and it is the common denominator of all transfer functions you can write between the signals in this loop. Having the transfer functions from the reference input and the disturbance to the output, we can write the output as the superposition of the contributions from these two inputs. At this point, let's assume that the transfer functions g1h and g1g2h are very large in magnitude. This can be achieved, for example, either by increasing the gain of the feedback h of s or the controller g1 of s. So you can neglect the unity terms in the denominators of the transfer functions defining C sub d and C sub r. This, in turn, means the transfer function C sub d by d is approximately 0. In other words, the output will not be affected by the disturbance at all. On the other hand, the transfer function from the reference input to the output will be approximately 1 over h. That means by changing h of s, you can impose any transfer function you like in the closed loop, whatever the planned transfer function g2 is. All these show us two important advantages of using feedback. Firstly, you can reduce the effect of disturbances, and secondly, you can also reduce the effect of changes in the plant dynamics to your output by applying feedback. And the higher your feedback gain, the better will be the disturbance rejection and robustness of your closed-loop system. Next, let us discuss briefly how we can draw and manipulate block diagrams. Whenever a physical system is given, drawing a block diagram of it involves two stages. 1. Finding the transfer function of each component, and 2. Assembling these blocks. Here is a simple electric circuit example. To draw the block diagram of this RC circuit with the input E sub I and the output E sub O, let us first derive the transfer functions of the components R and C. A resistive component can be described by the Ohm's law as I equals 1 over R multiplying E sub I minus E sub O. The Laplace transforms of these quantities are, of course, similarly related, which can be expressed as a block diagram like this. Also, writing the component equation relating the current to the voltage on a capacitor, we can express the transfer function of it as 1 over Cs. Now we have the block diagrams of all components in the system, and to get the overall block diagram, what we need is only to assemble them. Let us now summarize a couple of rules about how to combine and arrange components in a block diagram, namely the block diagram reduction rules. We start by combining cascade blocks. If you have two blocks, say G1 and G2 in cascade, and if you apply, say, signal A to the input, then the output will be G2, G1, A. The same output will also be obtained for a transfer function G2 times G1. That means two cascade blocks can be reduced to a single one representing the product of their transfer functions. Next, consider moving a block behind a summing point. If the inputs of a subsystem composed of a block and a summing point are A and B, then the output will be GA minus B. In order to maintain the same input-output relationships when the block G of S is moved behind the summing point, the input B has to be passed through a block of 1 over G. What if we move a block behind a branch point? Well, in this case, the block G of S has to be kept on both branches so that we can end up with the same input-output relationships. To see what happens in moving a branch point behind a block, let's again consider a fictitious input A and the corresponding outputs of this subsystem. So moving the branch point behind the block G of S would bring an extra 1 over G block to one of the branches. Another interesting case is when you have a feedback loop and you would like to move a block on the feedback path to the feed-forward path. Now, in such a feedback loop, for example, if the input is A and the output is B, the input to the G1 block in the feed-forward path happens to be A minus G2B. Now, if you move the G2 block to the feed-forward path, then we have to filter the signal A through the block 1 over G2 in order to keep the same input-output relationship as in the original feedback loop. Lastly, remember that we have derived the transfer function of a closed-loop system. So whenever we have a feedback loop with the feed-forward path as G1 and the feedback path as G2, we know that we can reduce it to a single block described by the transfer function G1 divided by 1 plus G1 G2. Note that in all such manipulations, the key principle is to keep the same input-output relationships in the subsystem that you are replacing. We can now apply such block diagram reduction rules on an example. Let us obtain the overall transfer function of this system by applying some block diagram algebra. Our aim here will be to arrange the blocks so that all feedback loops are either nested one in the other or completely separated from each other. We can reach such a configuration by moving the block G1 behind the summing point in front of it. Now, the order of 3 summing points can be arranged arbitrarily. So now we have all feedback loops as nested. We can now start simplifying from the innermost loop. That is a positive feedback loop with the feed-forward blocks G1 and G2 and the feedback block H1. Therefore, I can replace this part of the block diagram with a single block having the transfer function G1, G2 divided by 1 minus G1, G2, H1. Again, considering the inner negative feedback loop, we can reduce it to a single block and simplify it so that we now have a unity feedback closed-loop system, which in turn can also be represented as a single block and simplified as in the lower block diagram. Interestingly, the overall transfer function we have just obtained is in the following form. The numerator is a product of transfer functions in the feed-forward path. In the denominator, on the other hand, besides the term 1, we have a sum of transfer functions corresponding to each loop. Let's see them again. So this was our original block diagram. And this is the overall transfer function we obtained from the input R to the output C. The feed-forward blocks are G1, G2, and G3, and their product appears in the denominator. On the other hand, all loop transfer functions, that is, the loop of G1, G2, H1, the loop of G2, G3, H2, and the loop of G1, G2, G3 are appearing in the denominator. In the second part of the video, we will discuss an alternative way of modeling dynamic systems, namely the state space representations. To start with, let us contrast transfer functions and state space models. As we have seen earlier, transfer functions can be used in modeling linear, time invariant, and single input, single output systems. They are based on Laplace transforms, therefore they constitute a frequency domain approach to modeling dynamic systems. On the other hand, state space models can be used to model linear or nonlinear, time invariant or time varying, multi-input, multi-output, as well as single input, single output systems. Besides, they are time domain entities. In other words, they are differential equations in a special format. To explain the state space approach, first we need to define the concept of state. The state of a system is the smallest set of variables such that the knowledge of them at an initial time, maybe together with the knowledge of the input of the system, completely determines the behavior of the system for all future values. In other words, the value of the state at any instant summarizes the past of a system which is necessary to compute its future. As a simple example, consider this differential equation. Y double dot minus y dot equals u. Here u is the input of the system and y is the output. If the value of y and its derivative at time t sub 0 is known, then you can use these initial conditions to solve y of t from this differential equation. That is, you can obtain all future values of y and its derivative. This means y of t and y dot of t constitute a state for the system defined by this differential equation. If the state of the system involves more than one variable, like in this example, you can show them in a vector, which we are going to call the state vector and denote by a bold letter x. So the knowledge of the state vector at a particular initial time t sub 0 together with the future input values can be used to obtain the state vector for all values of t greater than t sub 0. Now consider a multi-input, multi-output system with r inputs from u1 to ur and m outputs from y1 to ym. The existence of a dynamic behavior in a system means that the future values of some signals in it depends on the past of the system, and hence requires existence of memory elements, that is, integrators. For example, integrators in a linear electric circuit are capacitors, which integrate current, or inductors, which integrate voltage. Since they accumulate past information, we are going to use the outputs of such integrators as state variables. Let's assume that we have n such states, that is x1 up to xn. Now, writing the state equations means expressing the inputs of these integrators, namely the derivatives of these state variables, in terms of the state variables, input variables, and maybe the time variable t. Similarly, you can also write the outputs as functions of the state variables, inputs, and time. Let us define the state vector x, the input vector u, and the output vector y, so that we can write all these equations as vector equations. So now we have two sets of equations. X dot of t is equal to a vector function f of x, u, and t, and y of t equals a vector function g of x, u, and t. The former is called as the state equation, whereas the latter is called as the output equation. In general, these equations are nonlinear. However, they can be linearized around a given operating point so that you can write them as x dot of t equals a of t x of t plus b of t u of t, and y of t equals c of t x of t plus d of t u of t. Here a, b, c, and d, which are functions of time, are matrices of appropriate dimensions. In fact, A is called as the state matrix, B as input matrix, C as output matrix, and D as direct transmission matrix or direct injection matrix. In this figure, you can see the interconnections of the variables u, x, and y representing this linear state space model. And besides the linearity, if the system is also time invariant, the state and output equations are of this simplified form, where A, B, C, and D are constant matrices. Our example for deriving state and output equations is a parallel RLC circuit. Here we have two integrating elements, namely the capacitor and the inductor. So the state variables are the capacitor voltage and the inductor current, and we have to express the derivative of these variables in terms of them and the input current. We can first write the element equation of the capacitor and then express the capacitor current I sub C in terms of I sub L, and V sub C. On the other hand, the element equation of the inductor directly relates the derivative of the inductor current to the capacitor voltage. We can combine these two equations in a matrix equation, and defining the state vector as V sub C I sub L, we can recognize this matrix equation as x dot equals A x of t plus B u of t. On the other hand, since the output is the capacitor voltage, it can be expressed as C times x of t, where C is a row vector written as 1, 0. Also note that in this case, the direct transmission matrix is 0. The next example is a mechanical one. An automobile shock absorber, in its simplest form, can be modeled as a spring mass damper system. In this figure, K is the spring constant, M is the mass, and B represents the friction coefficient. A differential equation describing this system can be obtained as a force balance equation. Namely, the input force can be written as a sum of three forces: the force to accelerate the mass, the force to overcome the friction in the damper, and the force to expand the spring. To obtain a state space model, we are going to choose our state variables as y of t and its derivative. In other words, the position and the velocity of the mass. Since the derivative of the position is the velocity, the first state equation will be written as x1 dot is equal to x2. And the derivative of x2, which is the acceleration, can be solved from the force balance equation. This gives us the second state equation. These two equations can now be cast in a matrix form where we can see the A and B matrices. Besides, the output is the position. The C matrix turns out to be composed of a 1 and a 0. And once again, in this case too, the direct transmission matrix is 0. Having discussed two alternative ways of modeling dynamic systems, namely the state space representations and the transfer functions, let's see how we can convert one of them to the other. We first start with writing transfer functions from state space models. To be able to write transfer functions, we have to assume that the state space model is linear, time invariant, and a single input, single output one. So we have constant A, B, C, and D matrices in our model with matching dimensions. We start by taking Laplace transforms of both sides in the system and output equations. Now arrange the system equations so that we have all x vectors on the left-hand side and collect them into a parenthesis of x so that we can solve for the x of s vector in terms of u. Now substituting what we have found for x of s into the output equation, we can solve for the ratio of y of s to u of s, which is the transfer function of this system. Note that the s variable appears only in the matrix Si minus A, which is inverted. That means g of s will be obtained as the ratio of two polynomials, and the denominator polynomial will be the determinant of Si minus A. So we conclude that any pole of the transfer function g of s must be an eigenvalue of the system matrix A. Let us now continue with our example mass spring damper system and obtain the transfer function from the state space description we have derived before. Recall the system and output equations of this system. We can use the formula expressing the transfer function in terms of the A, B, C, and D matrices. Substitute the matrices A, B, and C into this formula and rearrange the terms under the matrix inversion. It is not difficult to invert this matrix as its adjoint matrix divided by its determinant. Note that the polynomial in the denominator, that is s squared plus b over ms plus k over m, is the determinant of the matrix Si minus A. Performing the matrix multiplications and simplifying, we obtain the transfer function as 1 over ms squared plus bs plus k. Let's check this result with the differential equation we have written for this system before. By taking Laplace transforms of both sides under zero initial conditions, we can obtain the same transfer function between the output y and the input u. That shows the correspondence between the state space description and the transfer function we have derived for this system. Now we consider the inverse problem, namely obtaining a state space representation for a given transfer function. First, we will consider a relatively simpler case. That is, we will assume that the numerator of our transfer function is unity. If you write the differential equation corresponding to such a transfer function, you will have only the input function u on the right-hand side. Now, let us choose the state variables as the output and its derivatives. That is, the first state variable will be equal to y, and xn will be the n minus first derivative of y. If you differentiate these equalities, you will notice that the derivative of each state variable is simply the next state variable, and the derivative of xn, which is equal to the nth derivative of y, can be written from the differential equation in terms of the other derivatives of y or other state variables. To obtain the system equation, you only need to write these equations in a matrix form. And the output equation is simply a rephrasing of the equation y is equal to x1. So now that's our A matrix. This is the B matrix. and that turns out to be the C matrix. Let us consider the general case where we also have a polynomial of S in the numerator of our transfer function. We have here the most general case where the numerator and the denominator polynomials are of the same degree. But if the system is a strictly proper one, of course, some of the coefficients in the numerator like b0, b1, etc. will be 0. That means the differential equation for this system will have also the derivatives of u on the right-hand side. Since no derivatives of the input variable are allowed in the state space description, we are going to choose our state variables as follows. Starting from x1 equals y minus beta 0 u, each state variable will be composed of not only the derivative of the previous one, but also a contribution from the input u. So x2 will be x1 dot minus beta 1 u, and likewise xn will be xn minus 1 dot minus beta n minus 1 u. And since xn dot will be a combination of the nth derivative of y and all the derivatives of the input u, using the differential equation, it must be possible to write it as a linear combination of the derivatives of y and the input, or the state variables and the input for some suitable set of betas. To solve for such a set of beta parameters, you can use this last equation and substitute all the state variables x1 to xn as expressed with the derivatives of y and u, and then compare it to the parameters in your differential equation and solve the beta parameters in terms of a and b coefficients. Once you have determined your betas, the only thing that remains is to write all these equations so that you have y and the derivatives of the state variables on the left-hand side and rearrange everything in a matrix form. We see that we obtained the same system matrix. That's natural because the system matrix depends only on the denominator polynomial, that is the a parameters. On the other hand, the input matrix is composed of the betas. Also note that the state space description will have a direct injection term, that is beta 0 u, only if the degree of the numerator polynomial is equal to the degree of the denominator polynomial in the transfer function. Here we have an alternative way of obtaining a state space description from a transfer function, namely by a block diagram approach. Let's see this on an example. Here we have a transfer function with its denominator in a factorized form. It's a fairly general one. There are first-order factors in the numerator and the denominator. There is a second-order factor in the denominator, and there is also a 1 over s, that is an integrating factor in the transfer function. To start with, we can show the block diagram of such a transfer function as consisting of 3 blocks. And now our aim is to express the entire block diagram using only integrator and constant gain blocks. For example, this part corresponds to the block with the transfer function s plus z over s plus p. This is how you can express a second order block in terms of only integrators and constant gain blocks. And finally, the third block is an integrator by itself. So we have a block diagram for this transfer function where all blocks are either integrators or constants. We are going to choose the outputs of these integrators as the state variables. Their inputs will then be the derivatives of our state variables. Using the interconnections in the block diagram, we can express the derivatives of the state variables in terms of the state variables and the input. You can write such equations first in frequency domain and then translate them to time domain, or you may prefer to write them in time domain directly. finally collecting them in a matrix form, you can have your system equation and output equation corresponding to your transfer function. And that concludes our discussion of mathematical models of dynamic systems. Going over the examples and exercises in your textbook, check that you can distinguish between linear, nonlinear, and time-varying, time-invariant models, that you can derive transfer functions of simple electrical or mechanical systems, that you can use block diagram algebra to simplify block diagrams, that you have an understanding of the concept of state, that you can derive state space models of simple electrical and mechanical systems, and that you can obtain transfer functions from state space representations of linear systems, and vice versa.